Hello, my dear, and welcome to our astronomy course. Today, we are continuing study the death of stars. How do you see? What evidence can you cite to show that large number of stars die by producing planetary nebulae? You can begin your argument by noting that planetary nebula are only a light year or so in radio, and that the Doppler shift shows that they are expanding at 10 to 20 kilometers per second. Dividing the radius by the velocity tells you that a typical planetary nebula is only about 10,000 years old. And that means that the nebula don't last very long. Nevertheless, astronomers find 150 of them visible in the sky to be so common, but so short-lived. Planetary nebula must be produced in large numbers of medium-mass stars blow their outer layers into space. Now, review more evidence. Use favorite star theories to explain how you know that white dwarfs are very dense. Stars is binary systems that can evolve independently of each other if their orbits are enough. In this situation, one of the stars can swell into a giant and collapse without disturbing its companion. But some binary stars orbit as close to each other as 0.1 astronomical units. And when one of those stars begins to swell into a giant, its companion can suffer in peculiar way. And these interactive binary stars are interesting in their own right. The stars share a complicated history and can experience strange and violent phenomena as they evolve. But such systems are also important because they can help astronomers understand the ultimate fate of stars. In the next module, you will see how astronomers use interacting binary stars to search for black holes. Binary stars can sometimes interact by transferring mass from one star to the other. The gravitational field of the two stars, combined with the rotation of the binary system, define a dumbbell-shaped volume around the pair of stars called the Roche law. The surface of this volume is called the Roche surface. The size of the Roche loop depends on the mass of the stars and the distance between the stars. If the stars are far apart, the loops are very large, and the stars easily control their own mass. But if the stars are close together, however, the loops are small and can interfere with the evolution of the stars. Matter inside each star Roche alone is gravitationally bound to the star. But matter that leaves a star Roche alone can fall into the other star or leave the binary star completely. The Lagrangian points of the place are places in the orbital plane of a binary star system, where a bit of matter can reach stability. For astronomers, the most important of the points is the inner Lagrangian point where the two Roche meet. Let's look at this figure, please. If matter can leave a star and reach the inner Lagrangian point, it can flow onto the other star, right? From the Lagrangian to another. And thus, the inner Lagrangian point is the connection through which the stars can transfer matter. In general, there are only two ways matter can escape from a star and reach inner Lagrangian point. First, if a star has a strong stellar wind, some of the gas flowing away from it can pass through the inner Lagrangian point and be captured by the other star. And second, if an evolving star expands so far that it fills its Roche lobe, which can occur if the stars are close together and the lobes are small. And then matter can overflow through the inner Lagrangian point onto the other star. Mass transfer driven by a stellar wind tends to be slow, but mass can be transferred rapidly by an expanding star. Mass transfer between stars can affect the evolution of the star in a surprising way. In part, it is the solution to a problem that puzzled astronomers for many years. In some binary systems, the less massive star has become a giant, while the more massive star is still on the main sequence. If higher mass stars evolve faster than lower mass stars, how do the lower mass stars in such binary manage to leave the main sequence first? This is called the Algol paradox. After the binary system Algol, as you can see in this slide. Mass transfer explains how this could happen. Imagine a binary system that contains a 5 solar mass star and a 1 solar mass companion. The two stars form at the same time, so the higher mass star, evolving faster, leaves the main sequence first. When it expands into a giant, however, it fills its Roche lobe and transfers matter to the low mass companion. The higher mass star loses mass, and evolves into a lower mass star, and the companion giant mass and becomes a higher mass star that is still on the main sequence. This explains how there could be a system such as Algol that contains a 5 solar mass main sequence star and 1 solar mass giant. The first 4 frames of this figure show mass transfer producing a system like Algol. The last frame shows an additional stage in which the giant star has collapsed to form a white dwarf, and the more massive companion has expanded and is transferring matter back to the white dwarf. Such systems can become the site of tremendous explosions. To see how this can happen, you need to think about how mass falls to a star. Matter flowing from one star to another cannot fall directly into the star. Rather, because of conservation of angular momentum, it must flow into a whirling disk around the star. Angular momentum refers to the tendency of a rotating object to continue rotating. All rotating objects possesses some angular momentum, and in the absence of external force, an object maintains or conserves its total angular momentum. An ice skater takes advantage of conservation of angular momentum by starting a spin slowly with her arms extended and then warping them in. As mass becomes concentrating close to the axis of rotation, the spins more faster. The same effect causes the slowly circulating water in a bathtub to spin in a whirlpool as it approaches the drain. You may saw it in your own bathtub at home. Mass transfer through the inner Lagrangian point in a binary system toward a star must conserve its angular momentum. If the star is small enough, as in the case of a weird dwarf, the mass will form a rapidly rotating whirlpool called an accretion disk. Two important things happen in an accretion disk. First, the gas in the disk grows very hot due to friction and tidal force. The disk also acts as a brake, shifting angular momentum outward in the disk and allowing the innermost matter to fall into the white core. The interior parts of an accretion disk around a white core are violent flames. The temperature of the gas can exceed 1,000,000 Kelvin, causing the gas to emit X-ray, and the matter falling inward. It can produce a violent explosion when enough accumulates on the white. At the beginning of this module, you get that the word nova refers to what seems to be a new star appearing in the sky for a while and then fading away. Modern astronomers know that a nova is not a new star, but an old star flaring up. After a nova fade, astronomers can photograph the spectrum of the remaining faint point of light. Invariably, they find a short period spectroscopic binary containing a normal star and a white dwarf. A nova is evidently an explosion involving a white dwarf. After a few days, the spectral lines change to emission lines, telling you the gas has thinned. The blue sheet remains, and so you can conclude that an expanding cloud of debris has been ejected into space. Nova explosion occur when mass transfers from a normal star through the inner Lagrangian point into an accretion disk around the white dwarf. As the matter loses its angular momentum in the inner accretion disk, it settles onto the surface of the white dwarf and forms a layer of unused nuclear fuel, mostly hydrogen. As the layer deepens, it becomes denser and hotter until the hydrogen fuses into a sudden explosion that blows the surface of the white dwarf. Also, the expanding cloud of debris contains less than 0.300 solar mass. And it is hot, and its expanding surface area makes it very luminous. Nova explosion can become 100,000 times more luminous than the sun. As the debris cloud expands, cools, and sinks over a period of weeks and months, the nova fades from the explosion of this material hardly disturbs the white dwarf and its companion star. Mass transfer quickly resumes, and a new layer of fuel begins to accumulate. How fast the fuel builds up depends on the rate of mass transfer. You can expect nova to repeat each time an explosive layer accumulates. Many nova take thousands of years to build an explosive year, but some take only decades. The end of Earth. Astronomy is about us. Also, this module of our lecture has discussed the death of stars. It has also been discussing the future of our planet. The sun is a medium mass star and must eventually die by becoming a giant, possibly producing a planetary nebula and collapsing into a white dwarf. That will spell the end of the mathematical model of the sun suggest that it may survive for an additional 5 billion years or so. But it is already growing more luminous as it fuses hydrogen into helium. In a few billion years, it will exhaust hydrogen in its core and swell into a giant star about 100 times its present radius. That giant sun will be about as large as the orbit of Earth. So that will mark the end of our course. The sun's growing luminosity will certainly evaporate Earth's ocean, drive away the atmosphere, and even vaporize much of Earth's crust. Models predict that the expanding sun will eventually become large enough to totally engulf Earth. While it is a giant star, the sun will lose mass into space, and most of the atoms that were in the Earth will be part of the expanding nebula around the sun. If it becomes hot enough, it will ionize the expelled gas and light it up as a planetary nebula. Your atoms will be part of that nebula. There is no danger that the sun will explode as a nova. It has no binary companion. And as you will see, the sun is not massive enough to die the violent death of the massive star. The most important lesson of astronomy is that we are part of the universe and not just observers. The atoms we are made of are destined to return to the interstellar medium in just a few billion years. That is a long time, and it is possible that the human race will migrate to other planetary systems before them. That might save the human race, but our planet is hard. Let's see next scientific argument. How does spectroscopic evidence tell you what a nova explosion is like? For this argument, you need to use your knowledge of basic spectroscopy. As soon as a nova is seen, astronomers rush to telescopes to record spectra, and they see blue shifted absorption light. The blue shifts are Doppler shifts, showing that the near side of the object is coming toward Earth. The absorption lines must be formed by fairly dense cars seen through the cinegar, and much like the atmosphere of a star. So the surface of the star must be expanding rapidly outward. Later, the spectrum becomes an emission spectrum, and Kirchhoff's law tells you that the gas must have thinned enough to become transparent. The continuous blue shift shows that the expansion is continuous. And now review the false explosion evidence. How do observations of nova loom after they have faded provide evidence that white dwarfs are involved? Now, let's start another topic of today's lecture, the death of massive stars. You have seen that low and medium mass stars die relatively quiet as they exhaust their hydrogen and helium, and then drive away their surface layers to form planetary matter. In contrast, massive stars live spectacular lives. You may detail to meet this in this slide, and then destroy themselves in violent explosions. Stars on the upper main sequence have too much mass to die as white dwarfs, but their evolution begins much like that of their lower mass ones. They consume the hydrogen in their core and ignite hydrogen shells. As a result, they expand into giants, or for the most massive stars, supergiants. Next, their cores contract and fuse helium first in the core and then in a shell, producing a carbon-oxygen core. Unlike medium mass stars, the massive stars do become hot enough to ignite carbon fusion at a temperature of about 1 billion Kelvin. Carbon fusion produces more oxygen and neon. As soon as the carbon is exhausted in the core contracts and carbon ignites in a shell. This pattern of core ignition and shell ignition continues with the fuel after fuel, and the star develops the layer structure as shown in this slide, with a hydrogen fusion shell above, a helium fusion shell above, a carbon fusion shell above, shell and shell and shell. After carbon fuses, oxygen, neon, and magnesium fuse to make silicon and sulfur. And then the silicon fuses to make iron. The fusion of these nuclear fuels goes faster and faster as the massive stars evolve. Recall that massive stars must consume their fuels rapidly to support their great weight, but other factors also cause the heavier fuel, like carbon, oxygen, and silicon, to fuse at increasing speed. For one thing, the amount of energy released per fusion reaction decreases as the mass of the fusion atom increases. To support its weight, a star must fuse oxygen much faster than infused hydrogen. Also, there are fewer nuclei in the core of the star. By the time heavier nuclei begin to fuse, 4 hydrogens make a helium nucleus, and 3 helium make a carbon. Okay? So there are 12 times fewer nuclei of carbon available for fusion than there were hydrogen. This means the fusion of heavier elements goes very quickly in massive stars, as you can see from this table on this slide. Hydrogen core fusion can last 7 million years in 25 solar mass stars. But that same star will fuse the oxygen in its core in 6 months and its silicon in a day. Theoretical models of evolving stars, combining with nuclear physics, allow astronomers to describe what happens inside a massive star when the last of its nuclear fuels are exhausted. The death of a massive star begins with iron nuclei and ends in cosmic violet. Silicon fusion produces iron, the most tightly bound of all atomic nuclei. Nuclear fusion is able to release energy by combining less tightly bound nuclei into a more tightly bound nucleus. But once the gas in the core of the star has been converted to iron, there are no nuclear reactions that can combine iron nuclei and release energy. The iron core is a dead end in the evolution of a massive star. As a star develops an iron core, energy production begins to decline and the core contracts. For nuclei less massive than iron, such contraction heats the gas and ignites new fusion fuel. But nuclear reactions involving iron remove energy from the core in two ways. First, the iron nuclei begin capturing electrons and breaking into smaller nuclei. The gas is so dense, it is degenerate, and the degenerate electrons help support the core. The loss of some of the electrons allows the core to contract even faster. And second, temperatures are so high that the average photon is a high energy gamma ray, and these gamma rays are absorbed by atomic nuclei, causing them to break into the smaller fragments. The removal of gamma rays also allows the core to contract even faster. Also, the core of the star cannot generate energy by nuclear fusion. It can draw on the tremendous energy stored in its gravitational field. As the core contracts, the temperature shoots up, but it is not enough to stop the contraction. And the core of the star collapses inward in less than a tenth of a second. This collapse happens so rapidly that the most powerful computers are unable to predict the details. Consequently, models of supernova explosions contain approximations. Nevertheless, the models predict that the collapse of the core produces an immense supernova explosion in which the star's outer layers are blasted out. The core of the star must quickly become a neutron star or a black hole, the subject of the next model. To understand how the inward collapse of the core can produce an outward explosion, it helps to think about a traffic jam. The collapse of the innermost part of the degenerate core allows the rest of the core to fall inward, creating a tremendous traffic jam, as all of the nuclear fall toward the center. If it is as if every car owner, like in French Paris, suddenly tried to drive into the downtown of Ukrainian capital Kyiv. There would be a traffic jam not only downtown, but also in the suburbs, right? And as more cars arrive, the traffic jam would spread outward. Similarly, also the innermost core collapses inward. A shock wave, like a traffic jam, develops and moves outward through the rest of the star. The shock wave moves outward through the star, aided by two additional sources of energy. First, when the iron nuclei in the core are disrupted, and they produce a flood of neutrons. In fact, for a short time, the collapsing core produces more energy per second than all of the stars in all of the galaxies visible in the universe. And 99% of that energy is in the form of neutrinos. And this flood of neutrinos carries large amounts of energy out of the core, allowing it to collapse further, and helps heat the gas outside of the core and accelerate the outward bound shock wave. The torrent of energy flowing out of the core also triggers tremendous turbulence, and intensely hot gas rushes outward from the interior. Let's look to this slide, please. Again, this rising hot gas carries energy out into the envelope and helps drive the shock wave out. Within a few hours, the shock wave passes outward through the surface of the star and blasts it apart. The supernova seen from Earth is the brightening of the star as its distended envelope is blasted outward by the shock wave. As months pass, the cloud of gas expands, thins, and fades, and the rate at which it fades matches the decay rate of certain radioactive nuclei produced in the explosion. The violence in the outer layer can create densities and temperatures high enough to trigger nuclear fusion reactions that produce as much as half a solar mass of radioactive nickel-56. The nickel gradually decays to form radioactive cobalt, which decays to form normal iron. Essentially, all of the iron in the core of the star is destroyed when the core collapses, but more iron is produced in the outer layers, and that releases energy that keeps the supernova going. The presence of nuclear fusion in the outer layers of the supernova testifies to the violence of the explosion. A typical supernova is equivalent to the explosion of 1,028 megatons of TNT, about 5 million solar masses of hive explosion. But of course, the explosion is entirely silent. It is a common misconception promoted by science fiction movies and television that explosions in space are accompanied by sound. You know that that's not true, right? Because space is nearly a perfect vacuum, and sound can't travel through a vacuum. Supernova explosions are among the most violent events in nature, but they are silent. Collapsing massive stars can trigger violent supernova explosions. There is, however, more than one kind of supernova. Let's study types of supernova. In studying supernova in other galaxies, astronomers have noticed that there are a number of different types. Type 2 supernova have spectra containing hydrogen lines and appear to be produced by the collapse and explosion of a massive star. The process discussed in the previous section. I hope you remember that, right? The hydrogen lines are produced by the outer layers of the star, which are rich in hydrogen. Type 1 supernova have no hydrogen lines in their spectra, and astronomers have found at least two ways of supernova could occur and lack hydrogen. Type 1a and type 1b supernova. A type 1a supernova occurs when a white dwarf gaining mass in a binary star system exceeds the Chandra-Shikar limit and collapses. The collapse of a white dwarf is different from the collapse of a massive star because the core of the white dwarf contains usable fuel. As the collapse begins, the temperature and density shoot up, and the carbon-oxygen core begins to fuse in violent nuclear reaction. In a flicker of a stellar lifetime, the carbon-oxygen interior is entirely consumed and the outmost layers are blasted away in a violent explosion that at its brightest is about 6 times more luminous than a type 2 supernova. The white dwarf is entirely destroyed, and no neutron star or black hole is left behind. No hydrogen light are seen in the spectrum of type 1a supernova explosion because white dwarfs contain very little hydrogen. The less common type 1b supernova is thought to occur when a massive star in a binary system loses its hydrogen-rich outer layer to its companion star. The remains of the massive star would develop an iron core and collapse. As described in the previous sections, producing a supernova explosion that lacked hydrogen lines in its spectrum. A type 1b supernova is just a type 2 supernova in which the massive star has lost its atmosphere. Astronomers working with the largest and fastest computers are using modern theory to try to understand supernova explosions. But the companion to theory is observation. So you should ask, what observational evidence support this story of supernova explosion? In Ed 1054, Chinese astronomers saw a gas star appear in the constellation we know as Taurus the Bull. The star quickly became so bright it was visible even in daytime, and then, after a month, it slowly faded, taking almost 2 years to vanish from sight. When modern astronomers tuned their telescope to the location of the gas star, they found a peculiar nebula now known as the Crab nebula for its many large shapes. In fact, the leg of the Crab Nebula are filaments of carbon that are moving away from the site of the explosion about 1400 kilometers per second. Comparing the radius of the nebula, 1.35 per second, with its velocity of expansion, reveals that the nebula began expanding 9 or 10 centuries ago, just when the gas star made its. The Crab Nebula is clearly the remains of the supernova seen in AD 1054, as you can look from this slide. And I want to say that in the next module, you will meet the neutron star found at the center of the Crab Nebula. The blue glow of the Crab Nebula is produced by synchrotron radiation. This form of electromagnetic radiation is produced by rapidly moving electrons spiraling through magnetic field and is common in the nebula produced by supernova. In the case of the Crab Nebula, the electrons travel so fast that they emit visual wavelengths. But in most such nebula, the electrons move more slowly and the synchrotron radiation is at ratio wavelength. By now, the high-speed electrons in the Crab Nebula should have slowed, but the synchrotron radiation at visual wavelength is still strong. That is evidence that the electrons are being energized by the neutron star at the center of the nebula. Supernovae are rare. Only a few have been seen with the naked eye in the recorded history. Arab astronomers saw one in at 1006, and the Chinese saw one in at 1054. European astronomers observed one in 1572, Tycho's supernova, and one in at 1604, Kepler supernova. In addition, the guest stars of at 185, 386, 393, and 1181 may have been supernovae. In the centuries following the invention of the astronomical telescope in 1609, no supernova was bright enough to be visible to the naked eye. Supernovae are sometimes seen in distant galaxies, but they are faint and hard to study. Then, in the early morning hours of February 24, 1987, astronomers around the world were startled by the discovery of a naked eye supernova, still growing brighter in the southern sky. Let's look at this slide. The supernova, known officially as SN 1987A, occurred only 53,000 parsecs away in the large Magellanic Cloud, a small galaxy near our own Milky Way galaxy. This first naked eye supernova in 383 years gave astronomers a ringside seat for the most spectacular event in stellar evolution. One observation of SN 1987A is critical in that it confirms the theory of Kokova. At 2 hours and 35 a.m. EST on February 23 in 1987, nearly 4 hours before the supernova was first seen. A blast of neutrinos swept through the Earth, including perhaps 20 trillion that passed harmlessly through each human body on Earth. Instruments buried in a salt mine under the Lake Erie and in a lead mine in Japan, though designed for another purpose, recorded 19 neutrinos in less than 15 seconds. Neutrinos are so difficult to detect that the 19 neutrinos actually detected means that some 1,017 neutrinos must have passed through the detectors in those 15 seconds. Further, the neutrinos arrived from the directions of the supernova, and thus astronomers concluded that the burst of the neutrinos was released when the iron core collapsed in a neutron star, and the supernova itself was seen hours later when the shock wave blasted the star's surface into space. Most supernovae are seen in distant galaxies, and careful observations allow astronomers to compare the behavior of the different types. Type 1a supernova, caused by the collapse of white dwarfs, are more luminous at maximum brightness and decline rapidly at first and then more slow. Type 2 supernova, produced by the collapse of massive stars, are not as bright as maximum. They decline in a more irregular way. Recall that type 1a supernova have no hydrogen lines in their spectra, but type 2 supernova do. SN 1987 A was a type 2 supernova. Also, its light curve is not typical, as you may see here. It was produced by the explosion of a hot blue supergiant rather than the usual cool red supergiant. Evidently, the star was a red supergiant a few thousand years ago, but had contracted and heated up slightly, becoming smaller, hotter, and bluer before it exploded. Astronomers believe that most type 2 supernovae are caused by the collapse of red supergiant. Also, supernova explosions fade to obscurity in a year or two. Expanding shells of gas mark the site of the explosion. The gas originally exploded at 10,000 to 20,000 kilometers per second and may carry away a fifth of the mass of the exploding star. The collision of that expanding gas with the surrounding interstellar medium can sweep up even more gas and excite it to produce a supernova remnant. The nebulous remains of a supernova explosion, let's see in this part. Some supernova remnants, such as Cassiopeia A, show evidence of jets of matter rushing outward in opposite direction. This may have been ejected as the rotating star collapsed, and conserving angular momentum spun up to very high speed. The first matter blown outward from such a rapidly rotating star could have emerged as jets from its core. Astronomers are just beginning to understand the details of such violent force. Supernova remnants look quite delicate and do not survive very long, usually a few tens of thousands of years, before they gradually mix with the interstellar medium and vanish. The Crab Nebula is a young remnant, only about 950 years old and about 8.8 light years in diameter. All the remnants can be large. Some supernova remnants are visible only at radio and X-ray wavelengths. They have become too tenuous to emit detectable light. But the collision of the expanding podcast with the interstellar medium can generate radio and X radiation. You saw in the previous modules that the compression of the interstellar medium by expanding supernova remnant can also trigger that formation. For this moment, I think it's enough. Any questions or propositions? I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.